Okay, so chapter 4. We're not doing a do now because I want to make sure that we have enough time to get through all the salient points of chapter 4. I know that you probably didn't have time to watch the video that I posted. It's a little over an hour, but you will still want to do that even after this live session. So we're going to go through chapter 4 in some detail, more than I would normally do, because I know you haven't had a chance to familiarize yourself with the material. So we're going to go through a little bit of a history lesson in terms of the models of the atom. And then we're going to do some practice problems and add some more concepts and some more calculations and things that we can do in this chapter. So it'll be a little bit of lecture first, and then we'll get to the more interactive part. So bear with me. I will try to ask you questions along the way to make sure you're still with me. So here we go. We're talking about the models of the atom. People have been discussing matter and what matter is made of for a very long time. So going all the way back to ancient Greece, there's a Greek philosopher named Aristotle. You've probably heard of him if you've taken a philosophy class or something like that. And he argued that matter is continuous. What this means is that you can break matter apart infinitely. Doesn't matter how many times you've done it. But there's another person who argued that matter is discontinuous. That at some point you can't divide matter anymore. It won't be matter. It's something else. And that point was called atomos. And that is where we get the name for the atom. So quite a bit of time passed. I'm sure people were thinking about the atomic theory. But it wasn't until 1803 that John Dalton published the first atomic theory. John Dalton did a lot of work in terms of observing nature and observing chemical reactions and things like that, and writing theories and laws. So he's done a lot in terms of atomic theory and observing things in biology, all sorts of stuff. He was a busy guy. This is his atomic theory. So there's 5 postulates, which is just another way to say there's 5 points. There are 5 things that he believes to be true about atoms. The first is that an element is composed of tiny, indivisible, and indestructible particles called atoms. Now, what we'll find out, and what you may already know if you've taken chemistry and you remember, is that atoms are divisible. You can divide them into subatomic particles. So that part he didn't exactly get right. But this was his theory. And in 1803, just thinking about matter and atoms was controversial. So you have to place this in the moment in history to really get an idea of how profound and important this atomic theory was. The second part of his theory is that all atoms of an element are identical and they have the same properties. So if you have an aluminum can or a piece of aluminum foil, all the aluminum atoms in those objects are going to be the same, and they're going to act the same with the same physical and chemical properties. Are we good so far? We've just described the first 2 points of Dalton's atomic theory. Cool. Now let's get through the other 3 because they're all kind of related. We can take these atoms of different compounds or different elements and form compounds. Again, that sounds like, well, duh, isn't that what chemistry is? But remember, 1803, this concept was brand spanking new. So that's revolutionary. Compounds contain atoms in small whole number ratios. So you're not going to have 3/4 of an atom or 0.7 of an atom. You're going to have whole number ratios of the different elements combining to make compounds. And you can take those same atoms and combine them in different ratios to form different compounds. So maybe you've done some chemistry and you've rearranged some bonds, broken some bonds, made some new ones. Or you can think about H2O is water. The ratio of hydrogen to oxygen is 2:1. If you change the ratio of hydrogen to oxygen to 1:1 or 2:2, you don't have water anymore. That ain't water I want to drink, because it's hydrogen peroxide. So two different ratios, the same elements, but we've got different compounds. So that's what he's talking about, that you can have atoms coming together in different ratios to form different compounds. So do the last 3 points make sense? We can make compounds, whole number ratios, and that you can mix and match to make new compounds. That's all we're saying here. So how we feel about Dalton's atomic theory? So when it comes to exam 2, which is soon, it's gonna be mostly multiple choice and concept questions. So you're gonna need to understand these 5 points and be able to ask questions about or answer questions about them. So some time passed, and now we have J.J. Thompson. He did some work with cathode rays to determine the charge to mass ratio of a cathode ray. And in doing so, he discovered these negatively charged particles. Eventually, those particles were named electrons. So J.J. Thompson is given the credit for discovering the electron. He had a lab of his own. And so he went on to train other people in physics. And some of those people had their own labs and they trained people. To me, that's an example of being successful. Not just, oh, I can make my own discoveries, but you're training up other folks to walk in your footsteps. So good on you, J.J. Thompson, even though you're very much dead. He also did work on coming up with a model of the atom. So everybody's out there trying to do their own work, trying to figure out, what is this atom made of? What does it look like? We can't look at it with our eye, but based on the observations we make about nature, can we put together some kind of model that describes the atom? His model, he called it the Plum pudding model. Maybe he was hungry or something, but he called it the Plum pudding model. And that just says that you've got this kind of sea of positive charge, which is the pudding. And then you have electrons, which are the plums, which are also raisins, okay? And those electrons are distributed evenly throughout this sea of positive charge. What we're also assuming here is that most of the atom is made of empty space. Based on the work that Thompson did, he figured out that electrons were kind of small. And so pretty much it's these tiny little dots of electrons, these plums, in a sea of positive charge. And all that stuff in between is just kind of empty space. So is everyone clear on what the plum pudding model of the atom is? So you will need to know these different models. We're really going to have 3 models of the atom before we get to the current model of the atom. So the Thompson model is the first model that you'll need to know, also called the plum pudding model. So no, he didn't give the positive charge a name. So it was just a sea of positive charge, a homogeneous sphere of positive charge. And then there's the negatively charged electrons within that. Does that clarify? Good. So we're going to jump forward in history a little bit and then jump back. So 1903 was when Thompson made his plum pudding model proposal. A few years after that, there's a man named Robert Millikan who determined the charge of an electron. And with this information, Thompson was able to calculate the mass of an electron and a proton. Okay. Now, we're alluding to a proton, which was not mentioned in the plum pudding model. I'm going to abbreviate PP. So something must have happened between 1903 and 1911 that caused people to think, hey, maybe there's some other particles that exist. Maybe this plum pudding model isn't an accurate description of what an atom is. In 1906, Ernest Rutherford, who was a former student of J.J. Thompson, had his own lab. And he and his student, Hans Geiger, they made up an experiment to test whether or not the plum pudding model was correct. It's usually known as the gold foil experiment. And the reason it's named that is because it uses a gold foil. Basically what they did was they set up an experiment to pass through big particles called alpha particles at a thin gold foil. And if the plum pudding model was correct, the particles should just pass through that foil because there's nothing there really to make these big particles deflect. They're not going to hit anything. Kind of like if you've ever used like a remote control car or anything like that, you're driving it around, it hits the wall and it bounces back kind of, So there's nothing that's massive like that wall that's going to make the particles deflect or scatter, change their direction if the plum pudding model is correct. This is a figure of kind of how they set up their experiment. So you have a source of these alpha particles and you shoot a beam at the thin foil of gold. And around it, you have something that allows you to detect where those alpha particles end up. Do they end up going straight through or are they scattered? What they saw, or their results, most of the alpha particles went straight through. No deflection. But some were scattered. or deflected. What that means is that there was something massive enough to make those alpha particles change direction. So let me know if that makes sense, because we kind of just went through a whole experiment here. So I'm going to kind of break it down again. The question was, is the Plum pudding model correct? Their experiment, we're going to shoot some big old particles at a thin foil of gold and see whether or not those particles get scattered or if they go straight through undeflected. And what they saw, their results, most of the particles went straight through the foil, but some were scattered, significantly so. And their conclusion is that there must be some kind of mass within the atom that's big enough and dense enough to deflect these alpha particles. Does that make sense to everybody? Are we good? Don't go to sleep on me yet. I know my voice is soothing. And it may not 100% make sense because you're being introduced to it for the first time. So you may not have heard about the gold foil experiment in high school chemistry. But I go into detail about it in the video that's already posted on YouTube. So make sure that you watch that. If you're like, I think I kind of get it. If you were to go over it a couple of times. Yeah. So the detail is probably more than you may have heard. The most important part is knowing what the results are and what the conclusion is. That there must be some kind of a dense mass within the atom that the Plum pudding model does not say anything about. So the Plum pudding model was proven to be wrong. And that's pretty much what this slide says, right? So most of the alpha particles pass through the foil because the atom is largely empty space. But at the center, there's something that's got all the atom's mass, pretty much, and that has been named the atomic nucleus. The nucleus contains the protons in an atom. It's also got the neutrons, but they didn't know about neutrons right away. So Rutherford proposed his own model of the atom. So this is our second model. The first one was the Thompson model. So that's his, his mentor, right? The Plum pudding model. And now Rutherford has his own model where there's this nucleus at the center of the atom. And then in the empty space around the nucleus, you've got these negatively charged electrons. Now, based on some calculations and things that they did, they figured out, okay, there can't just be protons. It's not just one thing that's in this nucleus. So that's where the idea behind neutrons came from. And that was a man named James Chadwick discovered the neutron. So that was kind of added on to this. But the idea of a central nucleus and then the electrons in the empty space, that's the Rutherford model. And that's pretty much what we have today. See, I'm just getting ahead of myself. So I have it here on the slide about neutrons, okay? So they were discovered by someone else, but it was predicted by Rutherford. So are we clear on the Rutherford model of the atom with the nucleus and then the electrons around it? That's what you should be familiar with if you've taken chemistry. We're going to try to keep pressing on so we can get through the regular lecture portion. So just know we've covered 2 models of the atom so far. So we're going to look at the subatomic particles. The terms electron, proton, and neutron are probably terms that you've heard before. These are the symbols that you're going to see me use throughout. So E with the negative sign, P with the positive sign, and N with the 0. And those reflect the relative charges that each of those particles have. The electrons are on the outside of the nucleus. The protons and the neutrons are on the inside. You don't need to know the relative masses, aside from knowing that electrons are super teeny tiny, they're small. And the protons and the neutrons are roughly the same size. There's a slight difference, but not enough of a difference for us to really care about it. So you'll need to know the information in this chart except for these numbers here. So you don't really need to know the numbers. Just know that the electron is super small and the protons and the neutrons, they're about the same size, and they are what contribute the most to the mass of an atom. So are we good on the subatomic particles, electrons, protons, and neutrons? Good. So we need to talk a little bit about atomic notation. We've been talking about atoms, and in chapter 3, we introduced the periodic table a little bit. The periodic table, that's where all the elements are organized. And there's a lot of information you can get from that periodic table. And that's what we're building up to do. So chapter 4, we're building our ability to read the periodic table. And then chapter 5, we're going to dig into it a little bit more to look at the different trends and things on the periodic table. So chapter 4 is really, you need to understand chapter 4 so that when we get to chapter 5 next week, we can build. So atomic notation. This is where we're taking the symbol of an element and we're giving some extra information. The first piece of information we're going to cover is the atomic number, which is also known as Z. You will see it down here at the bottom as a subscript. And all the atomic number is the number of protons in the nucleus. It's the number of protons that distinguishes one element from another. At the top in the symbol, as a superscript, is what's called the mass number. The mass number is the protons in the nucleus plus the neutrons. So if you add up the protons plus the neutrons, that gives you the mass number. That really comes into play when we're talking about isotopes, and we're going to talk about those a little bit later. The third piece of information that you can get, or at least it's implied, from atomic notation, only for neutral atoms, is the number of electrons. So protons are positively charged, Electrons are negatively charged. In a neutral atom, you have the same number of protons as you do electrons, so that the net charge of your atom is 0. What does that mean? Let's say that you have carbon. Let me not write it like on the periodic table. This is carbon. That 6 is the number of protons, which is the atomic number. In order for this atom of carbon to be a neutral atom, it also has to have 6 electrons, because the 6 positive and the 6 negative cancel out. Does that make sense in terms of the number of protons being related to the number of electrons? We're going to do some practice on this, but I want to make sure that it's clear before we move on. Yeah, I can repeat that. I'll just use a different example too. Let's say that we have nitrogen. Nitrogen has an atomic number of 7. Mass number, let's say it's 14. That 7 is the atomic number, which tells me how many protons. If we're dealing with a neutral atom, then that means that there's 0 net charge. Because remember, we've got protons, which are positively charged, and electrons, which are negatively charged. In order to have a neutral atom with 0 charge, we have to have the same number of positive particles as we do negative. So if we have 7 protons, then we have to also have 7 electrons. So the atomic notation doesn't tell you directly how many electrons you have. But if you have a neutral atom, you know, based on the atomic number, how many electrons you have. Does that clear it up for you? Good. We're going to quickly cover isotopes, and then I have a practice for you to do. Now, you're not going to get information from the periodic table on isotopes. You're not going to see the mass number listed on the periodic table. We care about isotopes when we're talking about atoms of the same element that have a different number of neutrons. For example, there's carbon 12, where this 12 is the mass number. But you will also find carbon 13. They both have 6 protons, but carbon 12 only has 6 neutrons. Carbon 13 has 7. That difference means that they are isotopes. Does that make sense about what an isotope is? Okay. So when we're looking at the notation for 2 isotopes, we could see, if we stick with our carbon example, that's carbon 12, and that's carbon 13. Mass number is at the top. Atomic number is at the bottom. Let's do some practice. You'll need a periodic table. We'll start with 5 minutes and see how far you get. If you don't have a periodic table, if you don't have a textbook, you can go to the chapter 4 folder and pull up that PDF of the periodic table. That's the same periodic table that you will get with every exam. So you didn't really need one for the first exam, but I think I gave it to you anyway, maybe. But for all the other exams, you're going to need one. That's the exact one you're going to get every time. It's got the element names, the symbols, the atomic number, and the atomic mass, which we have not talked about the atomic mass yet. But you'll need a periodic table to complete this activity. To get everyone started on the same page, what you have to do here is fill in the information that's missing for each row. So in each row, you're going to have to do atomic notation, just like we did. So the example of that would be our carbon example, where you put the mass number at the top and the atomic number at the bottom, and you have to find the symbol for the element on the periodic table. How can we figure out which element it is that we're looking at? Out of all of these other characteristics listed here, what thing will tell us which element we have? The atomic number, which is the same thing as the number of protons. So it's repetitive. So does everybody see that? If you have the atomic number or the number of protons, then you can take that to the periodic table and find the chemical symbol for the element. And then after that, you have to know the relationship between the mass number and atomic number, neutrons, and things like that. So I will give you 5 minutes to work on it, and then I'll check in and see if you need more time. So I have 2:43 right now. Get out your periodic table, and I will check back in with you at 2:48. So there's about 30 seconds left until 2:48. If you need more time, you can raise your hand or say, wait, and I can give you another couple of minutes. Otherwise, if you're good, you can say you're ready. Okay, I'll give you 1 more minute. All right, let's get started. For the first row, what element did you get? You can just put the symbol. What element did you get? You should have gotten F for fluorine. And you know that by going to the periodic table and finding the element that has the 9 above it for the atomic number. Since we know the atomic number, we can fill it in on our notation. Now, I'm not going to ask you to add that into the chat because it'd be a struggle. But you can see what it looks like on your screen. Because we know the atomic number, we can also fill in the number of protons. What did you get for your mass number? You should get 19. Remember that the mass number is the protons plus the neutrons. So 9 plus 10 gives you 19. Yeah, if ever there is a problem with my audio or something, let me know, because I won't know. I don't hear me the way you hear me. So the final part is the number of electrons. How many electrons does a neutral atom of fluorine have? It should have 9. We said that the number of protons is equal to the number of electrons in a neutral atom. I'm stressing that point because we are going to talk about ions, which are not neutral, but that's in chapter 5. So that was row 1. What element did you get for row 2? Exactly. You should have gotten P for phosphorus. Now the atomic number is blank, but the number of protons is not. So that is how you figure out what element you have. How many neutrons do we have in this atom of phosphorus? So the number of neutrons is going to be the mass number, which is abbreviated as an A, minus the atomic number, which is a Z. So I'll put that up here as well. It's a Z, that's A. So in this case, our mass number is 31. Our atomic number is 15. When you do that subtraction, you get 16 neutrons. And finally, how many electrons do we have? We've got 15. So it should be the same number as we have for the protons. Third row, what electron, good gracious, what element did we get? I've been talking all day, so my tongue ain't working right, y'all. We got nickel. We already know the atomic number, and that's going to also tell us the number of protons. For your mass number, you should have gotten 59, which is the sum of the number of protons and the number of neutrons. And for the number of electrons, it should be the same as the number of protons, 28. So how do we feel about that practice? You do not round. There are no sig figs in the land of mass numbers and things like that. The mass number is not something that you find on the periodic table. You have to add the protons plus the neutrons. So 28 plus 31 gives you 59. Other questions? If you can fill in a table like this, then that means you understand the relationship between atomic number and mass number, number of protons, neutrons, and electrons. So you understand the subatomic particles and how they relate to each other, okay? So if there are no other questions, we are going to move on. Let's talk about atomic mass. So on your periodic table, we're going to use carbon again as our example. The number above the symbol is the atomic number, which is abbreviated Z. Below that, you'll see a decimal. That's the atomic mass. That is the weighted average mass of all the known isotopes of an element. So if we looked at all of the carbon-12 and all of the carbon-13, and we took into account what percentage of carbon is carbon-12 and which percentage is carbon-13, then we can calculate the weighted average. So what does that mean? I feel like it's better to go through a problem and then you'll get an idea of what the atomic mass is in terms of the weighted average. This is the same problem that I go through in the chapter 4 video that's already posted to YouTube. So you'll get to hear it twice. Hopefully that will mean that you understand it more the second time. So like I said, when we were discussing isotopes, each element has a different number of naturally occurring isotopes. Gallium has 2 isotopes, gallium-69 and gallium-71. They each have a mass and a percent abundance. The percent abundance just tells you out of all the gallium in the world, what percentage of it is going to be gallium-69 and what percentage of it is going to be gallium-71. The question asks, what is the average atomic mass of gallium? So we're calculating that decimal number that you see on the bottom underneath the chemical symbol. Before I touch a calculator, I like to organize the information that I'm given in a table. You may not be given all of the percentages to do this problem, but you need to remember that all of the percentages should add up to 100%. And I'll show you what that means as we're going along and doing the problem. But the first step is just organizing all of your information. In this problem, there are only 2 isotopes, but there could be and will be more. So you may not think it's necessary to do a table because there's only 2, but if you get into the practice of making the table when there are more isotopes, you will not get lost. You don't want to lose any of the information that you're given in the problem. The next thing I do is write in my percent abundance. For gallium-69, it's 60.11%. For gallium-71, it's 39.89%. All of these percentages should add up to 100%. What if in the problem I didn't give you this 39.89%? How could you figure out what the percent abundance is for gallium-71 if I didn't tell you outright what it is in the problem? Right. You would subtract the what you have from 100%. So if you have 5 isotopes and you know the percent abundance for 4 of them, then you would take all those 5 isotopes or 4 isotopes that you know, add them up, subtract that from 100. What's left over is the missing percent abundance. Yes, what is your question? No, because then you can't do it. So I've made a mistake. No, you should only be missing 1. If there's 2, then you'd be expected to read my mind. And that's not fair. You're welcome. So the second column I'm going to leave blank for now. We're going to go back and fill that one in. The third column that I write down is the atomic mass that's associated with each of these isotopes. Now you know I like my units because naked numbers are sad numbers. It's not going to be summer forever. Those numbers are going to be cold, out here in wintertime, with nothing to keep them warm. So use your units. AMU, atomic mass units. That's what atomic mass is measured in. So when you give your final answer for a problem like this, I need to see AMU at the end of it. Gallium-69 has a mass number of 68.926 AMU. And gallium-71, a little bit heavier, 70.925 AMU. Now we're going to address this column in the middle. What I like to do is express the percent abundance as a decimal. And this is going to be key to putting it into your calculator. So if we have 60.11%, how do we write that as a decimal? You take the decimal and you move it, let me use a different color here, 2 places to the left. That's the equivalent of dividing by 100. So that's what you can do to go from the percentage to the decimal. So what would my decimal be for 39.89%? .3989. The only thing that's left is the calculation. So what you're going to do is multiply your percent abundance expressed as a decimal by the atomic mass. You're going to take that product and add it to the product of your second isotope percent abundance as a decimal multiplied by its atomic mass. So when you write that out as one equation, it looks like this. This first part is the contribution of the gallium-69 isotope. The second part is the contribution from the gallium-71 isotope. You add those two together, and that will give you your atomic mass. That is the weighted average. Put that in your calculator and see what you get. So your calculator is going to tell you this number. How many sig figs can we have here? We can have 4 sig figs. So our answer would be 69.72 AMU. Yes. What is your question? No. So you could put in the gallium-71 first and then the gallium-69. You'll get the same thing. No. As long as you make sure that you're multiplying the correct percentage that goes along with the atomic mass, you can put the atomic mass first and then the decimal. Doesn't matter as long as the pair is correct. I do it this way because it makes the most sense for the table. So you're literally taking what's on the table and putting it into your calculator. If it makes sense to you a slightly different way, that's totally fine. All I'm doing is introducing the way that I do because it keeps things organized and there's no doubt about what you need to put into your calculator. So is that clear to everybody? So how do we feel about this type of problem? I know it's our first time we're running through one. Do you feel like if you had another practice that you might be able to do it? So I don't think we're going to have time to do another example of this type in this class. But if you need to go through another one, we can do that during office hours. There is a video. There's a video for this. It's posted. I just didn't get to post it as early as I wanted to. So there's a chapter 4 folder on Blackboard in course content that has the link for the chapter 4 video, the notes. It's got a video for electron configurations, which we're going to get to. And it's also got additional problems for you to do and an answer key for those problems along with your chapter 4 check-in. So all that stuff is up there. So this is a good time for a short break. We're going to be switching gears a little bit within chapter 4 to start looking at electrons and more of the structure of the atom. So we'll take a 5-minute break here and then we'll come back to it. So it's going to be 3:10 soon, so let's just say 3:15. So I'll see you in 5. All right, y'all. It's 3:15. I know it's a short break. I want to have one more practice that's on the concept of isotopes and atomic mass. And then we'll move on to the next topic. For this question, you should not have to use a calculator. Given the only naturally occurring isotope of fluorine is F19, determine its mass from the periodic table. I'll give you about a minute and a half to think about it, and then I'll share the answer. Okay. So there's only one naturally occurring isotope of fluorine. That means that the atomic mass listed on the periodic table only accounts for the one isotope. So the mass of the one isotope of F19 has to be the same as what you see on the periodic table. So it's 19 atomic mass units. Does that concept make sense? I typically have a question like that. So on my periodic table, it says 19.00. I'm not using the same periodic table as y'all have. I'm using the one from the textbook. But whatever, everyone would have the same one. So for the answers, I'll use the one from the textbook, okay? So I'll repeat it. There's one isotope of fluorine. So that means the weighted average, there's only one isotope. So that isotope, the mass of it, it has 100% abundance. All of the fluorine has that mass. So the mass that's on the periodic table is also representative of that one isotope of fluorine. I usually have a question like this on the exam. So that's why I try to give it as a practice. And you'll also see a question like this on your exam review for exam 2. It's one of those questions that that sounds like it should be a complicated answer, but it's actually one of the easiest questions that you'll get because all you have to do is look at the periodic table and put down what it says. So we're going to move away from isotopes and atomic numbers and things like that and go back kind of into the abstract land of talking about electrons and their properties and the energy associated with electrons. We're also going to add to the models of the atom that we've started on. So no, going back to that, the naturally occurring part, that just tells you out in nature, this is what you see. But the only means that there's only one isotope. The only naturally occurring isotope is fluorine-19. That's what tells you that there's only one isotope. Otherwise, you wouldn't be able to tell. Okay. So we're moving to abstract land. You may have encountered discussion about wavelengths, which the symbol for that is the lambda. You may have seen this in high school physics if you took physics. It may have been a discussion in chemistry if you took high school chemistry. But we're going to briefly talk about wavelengths, frequency, and energy. There's a longer explanation in the video. This is a bit more condensed. So I have some other slides and stuff, and we talk about each thing in detail. Here, I'm just going to kind of give you the overview. All of the light that exists is a part of what's called the radiant energy spectrum. It is a continuous spectrum. It's uninterrupted. And there are certain properties associated with long wavelengths of light and short wavelengths of light. The longest wavelength that you can encounter is the radio wave. So if you listen to the radio on your way to work or if you commute to campus, those are radio waves. They're very long, and they also have low energy and low frequency. I go through what a wavelength is and what frequency means in the video. So if you have questions about what those things are specifically, watch the video and it'll clarify. Right now, we're just going over the different wavelengths and their characteristics. So radio waves, long, low energy, low frequency. On the other side of the spectrum, there's cosmic rays. They are very short, they have high energy, and they also have a high frequency. So you will always see high energy and high frequency paired together, just like low energy and low frequency. Between radio waves and cosmic rays is everything else. So there's TV, the microwaves that cook your food when you're heating up your ramen noodles or whatever it is. Infrared, if you've ever used night vision goggles or anything like that, or you have an infrared camera, that's what it's detecting. Then there's the visible light spectrum. That's everything that we see with our eyes. So you may have learned the rainbow from lowest frequency and lowest energy to the highest. It's Roy G. Biv. Red, orange, yellow, green, blue, indigo, which is like a deep blue, and violet. You will need to know the relative order of all of these types of rays and the visible spectrum specifically. So you'll need to know your rainbow. Now, you don't need to know that violet light is 400 nanometers, but you do need to know that, for instance, red light has a longer wavelength than green light. So you'll need to know the relative order of these. Does that make sense for what you're going to need to know? So you're going to need to know long wavelengths means low energy and low frequency. Short means high energy, high frequency. And then you'll need to know the relative orders of these. So are we good on that? Let's do some quick practice just to make sure that we have the associations right. You will not get this on the exam, but since we're just going over it, I'm not trying to make you memorize it after looking at it for 3 minutes. So it's here for your reference now, and of course you can reference it when you're doing your homework, mastering chemistry, and all that good stuff. But for the exam, you need to know this relative order. So let's start with the first question. We're considering blue light and yellow light. For your answers, you can type in B for blue and Y for yellow. Of these two, which one has a longer wavelength, blue or yellow? is going to be the yellow. Yeah, you can abbreviate B or Y. It's fine. Which one has a higher energy, blue or yellow? It's going to be the blue one. So if the blue one is short, and this is relative, and the yellow light is long, the shorter wavelength is going to have higher energy. That means it's also going to have a higher frequency. Now let's compare infrared light and X-rays. So for that, you can put I or X. Which one has a longer wavelength? Infrared, right. Which one has the higher energy and, in turn, the higher frequency? It's going to be the X-rays for both. So that's the kind of comparison you're going to need to be able to do. If you can do that, you'll be good to go. Is that clear? Good. So taking into account this information, we can think about electrons as emitting light energy when they're moving around and doing things in an atom, when we're doing chemistry and stuff like that. This is our third model of the atom, the Bohr model. So he said that electrons are orbiting around the nucleus in fixed energy levels. Now, he got the fixed part wrong. They're not fixed. But there are definitely energy levels. And there are specific energy levels that electrons can be found in nowhere else. The word that we use for that is quantized. So if we have 3 different energy levels, you might be able to have an electron here, or it can be here. But there is no 1.5 or 2.7. That doesn't exist. It's either energy level 1, 2, or 3. Nothing in between. I talk more about what quantized means, and I give you some examples of quantized energy in the video. So as long as you understand the concept that with these energy levels, there is no floating in between energy levels. These are discrete energy levels that electrons exist in and nowhere else, then you'll be okay. When you move around from these energy levels, I'll redraw the 1, 2, and 3. Let's say that I have an electron in 1. I want to bump it up, give it a little bit of energy so that it can move up to level 2. I have to shoot it with a certain amount of energy. That is the right amount to get it to move from level 1 to level 2. If I have an electron that's excited, it's got some extra energy, it can fall back down and release a photon, aka light energy. So that's how we can kind of think about, that's why talking about the waveforms of light and kind of the different energy associated with them, that's the link there. And there's more information about that in the video. But when electrons move from one energy level to another, you have energy being put into the atom, or there's energy being released. And that leads us to, yeah, I can repeat that. Actually, I'm going to stay on this slide because that's really describing the quantum mechanical model, which is our fourth model. So if we have 3 different energy levels for our electrons, if we want to increase the energy, we're going to add some energy to the system. And that is going to allow our electron to jump up to a higher energy level. The way that that energy is delivered to the electron is a photon, or a packet of light. Because light is just energy. If we have an electron that's excited and it falls back down to what we call ground state, or just a lower level, then you're going to release a photon. That means you're releasing energy in the form of light. And there's evidence for this that I talk about, where each element has an emission spectra, which means if you excite it and then let those electrons go back down to where they normally are, their ground state, they emit light. And that light, you can see different colors. So it's kind of like an atomic fingerprint. And that's the evidence for electrons being able to move from one energy level to another, and that they emit energy when they are going from a higher or excited state back down to a lower state. If that doesn't 100% jive with you right now, that's okay. You don't need to understand that for us to move on. But if after the video you still don't get it, let me know. Is that fair? Okay. Because I want to make sure that we have time to get all the way through to doing some practice with writing electron configurations, because that is typically one of the more difficult things for students to do in this chapter. So I want to make sure that we have time to walk through that a little bit more slowly. So we're talking about electrons, and we have these energy levels. Now we're going to define these energy levels a little bit more. If you think about a mall, like an indoor mall, not a strip mall or something like that, but an indoor mall where there's multiple levels. Maybe on the first level, there's a food court and a carousel or something for you to put your kid on, and then they forget that they're at the mall. And then at the second level, maybe there's some clothing stores or anything like that. Uh-oh. Yeah, I see that it's reconnecting. There it is. Collaborate just decided to do its own thing. Y'all see it now? Okay. Okay, yeah. I don't know what happened there. So we're talking about the mall, which is more interesting sometimes than chemistry. No. So we've got different levels that you can go on. Level 1, level 2, level 3. But it's not just one big level. There's different stores, there's food court, there's kiosks in the middle of the mall. There's different places that you can go to that are defined within the mall. It's the same thing with orbitals. So we have what's called the main energy levels. Like I was drawing with the 1, 2, and 3. Those are main energy levels. But inside of an energy level is an orbital. In the main energy level 1, you're only going to find an s orbital. In energy level 2, you will find s and p orbitals. There's a total of 4 different types of orbitals. There's s, p, d, and f. And each main energy level has some combination of these available for electrons to live in. The higher your main energy level, the higher the energy of your orbital. So if you have a 4s orbital, it's higher in energy than the 2s orbital simply because 4 is bigger than 2. Orbitals are a little bit abstract, and just talking about them, trying to define them outside of doing an electron configuration can be a little bit difficult to understand. So I'm going to go forward a little bit, and then I'm going to check in to see if the concept of orbitals makes sense. So if it's still a little fuzzy now, that's okay. We're going to talk about it some more. So this figure is another kind of visualization of energy levels and sublevels. So the first energy level is designated 1s. Remember that you have your nucleus in the center, and all the electrons that are associated with that atom are in the empty space outside of the nucleus. The first energy level that electrons can be in is energy level 1. That's the main energy level. Within that main energy level, there is a 1s orbital. For energy level 2, the main energy level, you have 2 different orbitals, the 2s and the 2p. The s and the p, those have to do with the geometry and the definition of the orbitals and what they look like. So you don't need to worry about that. But the S, P, D, and F, they're actually acronyms for things. They're abbreviations. You don't need to know any of that. In the third main energy level, you have 3 different types of orbitals. The 3s, 3p, and the 3d. Notice that the 1s is very close to the nucleus. And relatively speaking, the 3s is far away. The further away those electrons are, the higher energy they have to have. So when we're comparing orbitals, and we're comparing, let's say, 1s versus 3s, the 3s is going to have higher energy because it's further out. Is it starting to make a little bit more sense about the concept of the different levels within a main energy level? Do you understand it a little bit more than you did in the previous slide? Because we're just trying to build. This is an abstract concept, and I know this is something that you don't really talk about in high school chemistry. So between this lecture, watching the live lecture, and doing practice problems, hopefully that'll get you there 100%. So the goal for today isn't, I can go take a test now. It's, okay, I think that kind of makes sense. I may still scratch my head a little bit, but I think I'm ready to hear it again and I can receive it a little bit better. That's the goal for today. So if we're getting there, then we're achieving our goal. This chart gives more information about the different energy levels. So we've got energy level 1, 2, 3, and 4. On the periodic table, what this corresponds to is the row number. So we're talking about row 1, 2, 3, 4. And there's actually 7 rows on the periodic table. So each of those rows, we're talking about different sub-levels that have certain orbital shapes. I'm going to write out for you what the order is that the electrons will fill all of these levels. But before I do that, I want to go over the concept of filling these orbitals with electrons. Let's say that I have 5 electrons and they all need a home. I can't just put them all in one orbital because that one orbital doesn't have the resources to take care of them all. So we look at the first energy level. It has an energy sublevel of 1s. That can hold 2 electrons. So that means that I can place 2 of my electrons out of the 5 into the 1s energy sublevel. That's all that 1 can offer. The main energy level 1 only can fit 2 electrons. I've still got 3 more electrons to put somewhere. So I have to go to the next energy level, main energy level, and that's level 2. The first sublevel that we're going to encounter is the 2s. Each s orbital can hold a maximum of 2 electrons. So just like with the 1s orbital, we were able to place 2 of our electrons into a home, we can again place another 2 electrons into a home with the 2s. But I've still got 1 more electron that needs a home. And it's getting sad because it's the last one to be adopted. You don't want to be the last one picked on the kickball team because that means nobody wants you. And that's really sad. So we have to get this electron somewhere. The next place that we're going to go is still within the main energy level 2. So it's the same neighborhood as the 2s, just a little bit further away. We're going to go to the 2p. And we're going to place 1 electron there because that's all we've got left. However, if we have more electrons that need a home, the p orbital can hold a maximum of 6 electrons. So if we have another 5 electrons that need to be adopted, we can stick them all into that 2p orbital before we have to move on. The other 2 orbitals that we need to address in terms of how many electrons they can hold are the d and the f. The d can hold a maximum of 10 electrons, and the f can hold a maximum of 14. So in this conversation of placing electrons and the different orbitals and energy levels, do you feel perhaps a little bit more comfortable with the idea of orbitals? A little bit more comfortable than on the last slide? If the answer is no, that's okay. but we're building up to writing an electron configuration. So what I'm going to do for you before what's your question, Patrick? Yes, that is exactly what we're building up to. So you're ahead of me. Stop looking at my notes. Get out my notes. Okay, so this was our little example about placing 5 electrons. And what we did inadvertently was write an electron configuration for boron, which has 5 electrons in a neutral atom. You're not always going to just have 5 electrons. And these orbitals don't fill in the same exact order that you see listed here. So what I'm going to write for you is the full electron configuration. I also do this in the video that is already posted to YouTube. Make sure that you have this somewhere in your notes, and that when you get lost writing an electron configuration, that you pull it out. I'm also going to plug the other video that I posted in the Chapter 4 folder. It is not my video. I did not make it. I do not know the individual who made it. I do not profit off of any of that. But it's a really good video that gives a visual of how to fill out an electron configuration. So after this, if you're still like, that video will help a lot. So if you have questions, go to that video for electron configuration. It's about like 7.5 minutes long. And why reinvent the wheel? I could do that too, but it would take me a lot longer. So watch that video too. It's really good. So here we go. This is the full electron configuration. So for the biggest element on the periodic table, this is what its electron configuration is. You're always going to start with the 1s, and it can hold 2 electrons. Then we start with the 2s, another 2 electrons. The 2p can hold a maximum of 6 electrons. We're back around to the s, and we're in the 3rd energy level. Notice how each s, I'm putting 2. That's the full number of electrons that an s orbital can hold. So it doesn't matter if it's 1s, 3s, 5s, they all can only hold 2 electrons. The same thing with the p. The 3p orbital can hold 6 electrons total, just like the 2p. After you fill the 3p, you actually fill the 4s orbital first. It is lower in energy than the 3d. And when you look at the periodic table, which we're going to do that in just a minute, and kind of define some of the blocks on the periodic table, the 3d block, that is actually in the 4th row on the periodic table. So the row tells you the energy level, and the 4s and the 3d are in the same row. Little bit confusing, but when you see it, when we write it all out, it will hopefully make a little more sense. After the 3d, you go back and fill the 4p. Then you go back around to the 5s. You dip back to the 4d. So that's the same pattern. Then you come back to the 5p. Again, I'm writing down the maximum number of electrons that you can hold here. After you fill the 5p, you fill the 6s. Then you go back and start filling the f's. And those can hold up to 14 electrons. Then you fill your 5d, then the 6p. Last row, you start with your 7s, then you fill your 5f, your 6d, and your 7p. So that is the full electron configuration. So this is the biggest element on the periodic table. This is what its configuration is. Make sure that you have this somewhere and you can reference it for the order that the orbitals fill in the different energy levels. We're going to take that information and put it on top of a periodic table. And then after that, I'll check in and see if there are questions. So we talked about the S, the P, the D, and the F. If you are any of the elements that I am boxing in black, then you are part of the S block. And that means that you are filling the S orbital in whatever energy level you're in. So this is energy level 1, 2, 3, 4, 5, 6, and 7. You'll notice that helium is on the other side of the periodic table. That's because it's a noble gas, and we haven't talked about some of the common names of the different groups and things like that. That's chapter 5. But I just want you to know it is still a part of the S block, and it is in the first row of the periodic table. So we're filling the 1s here. So at the electron configuration for helium would be 1s2. Now we're going to define our P block. Everything that I'm boxing in red is filling a p orbital. So the configuration with neon would end with 2p6. Helium is a noble gas. You don't need to know that for chapter 4. We're going to go over all of those names in chapter 5. So we're not done with the periodic table. It's just hard to talk about it without using some of that nomenclature. So I try to avoid it, but it's a little difficult. You're welcome. So we've got the S block in black. We've got our P block in red. Now let's talk about the D block. These are all of our transition metals. We're filling the D orbital here. So when you're writing out your electron configurations, this row has the 3D, 4D, 5D, and 6D, even though we're in the fourth row. So this would be 4S. Let me just write it in the right color. We're still with 3D. So hopefully this visual will help you understand. And likewise here, we're back to the 4P. The final block is the F block, which I didn't even plan that. Now it's located at the bottom of the periodic table, but it really fits in here. So you'll see this space, or you'll just see an asterisk or something that's saying, hey, between barium and, I'm not even going to try to pronounce this one because some of these names are kind of messed up, hafnium, there are all these other elements. So this top row of the F block, this is the 4F. The other one is the 5F. I highly, highly, highly recommend that you decorate a periodic table with this information. If you have color pencils or markers, anything like that, do it. Very muchly highly recommended because it will help you when you're writing electron configurations. And while you can't bring this to the exam, you can certainly recreate it on your periodic table, and that will help you. So how do we feel about the visualization of the periodic table with the different blocks? Is this helping to make those orbitals make more sense? Okay, this is always a tough topic, so I want to make sure we take the time. All right. Now we're going to try writing an electron configuration together. We're going to write a configuration for a neutral atom of copper. We're going to find copper. That's here. To write an electron configuration, we need to know how many electrons we need a home for. The atomic number for copper is 29. How many electrons are in a neutral atom? Think about the relationship of what the atomic number is. It's the number of protons, right? In a neutral atom, we have to have the same number. So that means we've got 29 electrons to place. Yeah, I don't know if it's just a delay with Blackboard or what. I was like, I think they should get this one. So we've got 29 electrons that need a home. We're going to start writing our electron configuration and walk across the periodic table until we get to copper. This is always going to be our starting point. We're in the 1s, and this is where having the order of the orbitals filling is helpful. So we're filling the 1s right now. We've got 29 electrons. The s can only hold 2. So we clearly need to keep going. Let's drop back down to the second energy level. We're back in the S block again, so remember your blocks. I'll throw them up here real quick. We're back in the S block, and we're filling that. There can only be 2 electrons there. So now we've got a total of 4 electrons placed. After we fill the 2s, we're now in the P block. How many electrons can we fit in the p orbital? We can fit 6. So this bottom one I'm going to put as our running total so we can keep track. So now we're at 10 electrons placed. We've still got 19 more to go. So we come back around and we go down to that third row. So we're in the 3s, because we're in the S block, and we can fill in 2 electrons. So that's here, okay? Oh, whoops, not there. Here. That's better. Then we jump across to the P block. And we can fit another 6. Now we're at 18 electrons placed. Still not done, but close. We go down to the 4th row. What block are we in now? What are we filling? We're filling the S. So we're in the 4s. How many electrons can I fit in an s orbital? I can fit 2. And since I'm only at 18 electrons, I need to put all the 2 in there. Now we're at 20. What do I fill next? Because right now, we're here. We're filling that 3D next. Because that's where we are. We're literally going across each row and writing out how many electrons can be held there until all of our electrons are placed. So we're in 3D, and then you just count. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we're at copper. And when you add all that up, you should get 29. Sure, I can go back to that for a second. Here's the labeled one. And if you want to be lazy, if you have a color printer, you can just print this out. You can just print this out from the PDF. Let me know when I can go forward. Oh, you're welcome. That was fast. All of these superscripts, when you add them up, you should get the total number of electrons that you have to place. And that's what I was doing here as we went along. It's kind of a good way to keep track of how many electrons you've placed and how many more you need to go. What's your question? Sure. So each orbital, the S, P, D, and F, can hold a certain number of electrons. The S holds a maximum of 2 electrons. The P holds a maximum of 6. D can hold 10, and F can hold 14. So that's something you're just going to have to know. Each orbital can hold a maximum of this number of electrons. That's where we're getting these different numbers from. The final one that we filled in, the 3D, we didn't fill the orbital all the way. The d orbital can hold 10 electrons, but we only had 9 left. So that's why we only placed 9 in the 3D. Does that help with understanding the different numbers there? Good. Are there other questions on writing electron configurations? If you're not like, yeah, I'm ready to go and do it, that's fine. I'm not expecting you to be there. But does this process make sense? Is it like, okay, I think I might be able to do that if I practice a little? And if your answer is no, or I don't know about that, that's fine too. Because we're going to walk through another example after this. And I'll ask you questions along the way. So let's go through another example. So copper, that was only 29. Let's do a bigger one. Neodymium. It's in the F block. It's got 60 electrons. So we're going to have to walk across a lot of this periodic table to get to neodymium. We always have to start at the beginning with the 1s. We can take 2 of our electrons and fill the 1s. After that, we've got to drop to the second energy level, the second row. I will again quickly label So I threw in the labels for the D's and the F's so that you can be placed a little bit better. I think the S and the P, that's a little bit easier to get. So we filled the 1s. Now we have to go to the second energy level, and we're going to fill the 2s completely. After we fill the 2s, what do we fill? We've got to fill the 2p. The p orbital can hold a maximum of 6 electrons. So now we're at 10 electrons that we've placed, but we've still got 50 more to go. That's not intimidating. So let's go on, and we move to the third energy level. And just to reinforce the concepts that we talked about a little bit earlier, as these energy levels get bigger and bigger, these electrons are further and further away from the nucleus. So they have to have a higher energy to stay associated with that nucleus in that atom. Oh, didn't mean to do that. All right. Whoops. Here we go. So now that we've filled the 2p, we have to fill the 3s. Then we hop over to the p block, and we fill the 3p. What do we fill after we fill the 3p? We're not at the D block yet. We are now we're going right across. So we are now in the 4s. Pay attention to what block you're in. That will tell you which orbital you're filling. We can fit 2 electrons into the s orbital. Now we're filling the 3d. From there, you fill in the 4p. So make sure you get that. Now we go to the 5th energy level, because we're still not there yet. So if we keep our tally going, we're at 36 electrons. The other way you can figure that out without doing the math, if you're walking across the periodic table, once you fill the 4p, you're at krypton, and that atomic number is 36. That means that you also have 36 electrons in a neutral atom. So now we're in the 5th energy level. We're going to fill our S. Then we're going to fill the 4D. Then we're going to fill the 5p. When we do that, we're here. So we've placed 54 electrons. We've still got 6 more to place. So we keep going to the s orbital in the main energy level 6. So we're pretty far down on the periodic table. You fill that, and then you run into this asterisk. That means you're going down here to the F block. And that's the home of neodymium. So we're now filling the 4F, and there are 1, 2, 3, 4 electrons that we have to place until we get to neodymium. So that is a long one, but I wanted to do an example of a long one so that you have it. How does that feel? If it's still a little shaky, that's okay. But do you feel a little bit better than before? Or if you felt good and you still feel good, that's good too. Yeah, writing it out definitely makes it easier. So, again, you need to decorate your periodic table with the different blocks. It may be helpful to write in the orbitals too. If it's still not making sense, watch the video and watch the video that I posted for electron configurations, because she does a good job of kind of visually doing it. She has these little pieces of paper and stuff that she cut out. And so it's like she's physically covering up the periodic table. So it's a cool video to give you that concept. I think it'll really help if doing it this way doesn't do it for you. So I have a couple of practice problems here. It's okay. If your connection is bad, it's fine. I see you going in and out of the room. I get it. The video will always be posted on Blackboard. So after this, well, I'm going to tell you the truth. I'm hungry. I didn't eat lunch because I have classes back to back. So I'm going to eat first, and then I'm going to make sure that these videos get posted this evening. So if there's any part that you missed, you can always go back and view it. I have these 2 practice problems here. I'm not going to have us do them now, but I will fill in the answers before I post the PDF. So you can use these as practice for yourself. So if you want to jot it down in your notebook or something like that, or just know that you can come back to it and do it, that's totally fine. But these practice problems will help you see what you know and what you don't know when it comes to electron configurations. You will need to be able to write them, but you should also be able to look at a configuration and figure out which element it corresponds to. So do that practice on your own time. I wanted to get to the reminders. So we have a chapter 4 check-in due on Sunday. It's already posted. There's 4 questions. There's also the Mastering Chemistry homework and quiz that's due on Sunday as well. So make sure you get both of those things done. And I want to stress, the Mastering Chemistry, that's a hard deadline. So if you don't finish that by 11:59 on Sunday, whatever you have there is what your grade's going to be. For the chapter check-ins, while you may lose points, you still have an additional week to turn it in. If you wait that whole week, so let's say you don't hand it in on the 20th, but instead you hand it in on the 27th, it will be worth half of the value. Each day you lose 7% of the point value that the assignment is worth. If you don't turn it in within a week of the due date, then that's it. So prioritize getting the Mastering Chemistry homework done if you have to choose one or the other, because those deadlines are set. The chapter check-in, I give you a little bit more flexibility. I know it's a lot of work to do, so I'm trying to give you some grace, even though I'm not giving you extra, time like that. So virtual office hours this week, again, we're going to do Wednesday, 12:30 to 2:30. But a lot of people have filled out the Respondus practice exam with their availability. So I'm still sorting through those to see when the best time would be. If the time that the majority of folks are available doesn't work for your schedule, you can always set something up by appointment. And that leads me to my next point. A lot of you have been emailing me, but we have to move to course messages. The university is being pretty firm on that. Use course messages in Blackboard in the course and communicate with me there. So what you have to do is there's a little button that has 2. Click on that, and then there's going to be a box with all the names of the people in the class, including me. I'm the instructor. I believe it says instructor next to my name. But either way, I'm there. Choose me. And then you can send me a message through course messages. And I won't respond to you being like, so what class are you in? Because I'm sure that's frustrating. But I don't have everybody in my head. I have over 100 students. That's a lot of people to remember. I get my kids' names mixed up. And I've got 3. So that just gives you a little bit of basis for what I'm going through right now. But please use course messages. From here on out, if you email me with a question, I will respond to you saying, hey, I'd love to help you, but you got to send this to me through Blackboard using course messages. I check that just like I check my email. If you're not clear on how to do that, let me know. The final thing is exam 2. I know we're just finishing an exam, but these exams are only covering 2 chapters. Exam 2 will cover chapters 3 and 4. So it is imperative that you do your homework and you ask questions. I've got extra practice problems posted for both chapters 3 and 4, along with answer keys for those. So use that as additional practice and ask me questions in office hours. I'll also be posting an exam review, just like I did the last time. and we'll try to work in some exam review next week. If you haven't finished exam 1 due to the outage with Respondus, and I didn't post until Monday that, hey, everything is fixed, because that's when I was told, you still have some time. You have to have everything completed by 5 o'clock tomorrow. So Wednesday, September 16th, 5 p.m., you need to have everything submitted, because it's going to disappear for good. After that, I will start releasing grades, because I know you all want to know. Are there any questions? Because that was quite a bit of information. Lots of dates, exams. If you have any questions, now's the time to ask. Otherwise, this is it. This is all I've got for you for Chapter 4. But please remember that you need to watch the video online too. I did not cover every single detail of Chapter 4 here. So if you're good, have a good one. Otherwise, I'll be here until everybody's gone.